Okay, another talk about the swirls. We're going to approach it from a different direction, though, here now. I'm talking about thermal infrared, mid-infrared observations of the swirls by the Diviner lunar radiometer experiment. And as with a lot of these things, this is a real team effort. A lot of folks on the Diviner team have contributed different pieces to this. Okay, so we've had a little bit of background already, but just to reiterate, in the recent and not too recent literature, there have been several mechanisms proposed to form the lunar swirls. They include what I'll call here abnormal space weathering, not a complete lack of space weathering, but abnormal space weathering where the magnetic fields protect the surface from charged solar wind particles, still allowing micrometeoroid bombardment. There have been ideas related to the impact by swarms of micrometeors or microcomets, which disturb the regolith, revealing unweathered subsurface materials and transporting fines. Electrostatic dust transport models where bright-ish feldspathic dust is lofted by electric fields generated as a terminator passes over the surface. This is Garrick Bethel et al.'s ideas. Then kind of more recently, Carly Peters has proposed kind of a hybrid dust lofting and magnetic sorting and fairy castle structure destroying model to account for the visible near-infrared spectral properties that she observes in the swirls. So I'm going to talk specifically, though, about data from the Diviner lunar radiometer. Many of you are familiar with the instrument, but specifically I'm going to talk about data from 3 channels near 8 microns. We can measure the emissivity at these 3 wavelengths and then fit parabolas to those, and the maximum of that fitted parabola is what we call the Christensen feature or the Christensen feature position, which is related to primarily composition and specifically the silica polymerization in silicates, but as we'll talk about, it's related to other things too, and that's why we can see swirls with a CF. So I had a paper come out earlier this year in Nature Communications, specifically looking at the CF anomaly, what I call CF anomalies at swirls. So we measure the CF position. We can plot that on a color map, and you can see here's Reiner gamma. They appear, this is on a scale from 8.15 to 8.45 microns. The swirls generally exhibit shorter wavelength CF positions than the surrounding material. So here's Reiner gamma. Here's Van de Graaff crater as well, which is near the Jenny swirls. And so the basic observation is that with Diviner, we see what appears to be a shift in the CF position to shorter wavelengths compared to the surrounding terrain. Here's that data displayed in a different way. So here's Reiner gamma again. So this is a histogram of a bunch of pixels on the swirl, a bunch of pixels off the swirl, and then interestingly, the dark lanes as well. It looks like the dark lanes do not look a whole lot different from the off-swirl pixels. We'll get back to what that means in a moment. And then here's just another one for Van de Graaff crater. So we're clearly separating. We see very clear separation in the CF positions between the swirls and the off-swirl positions. So we want to kind of understand what that means. We can try to correlate this with things like Paul Lucey's optical maturity parameter. And when we do that, so higher OMET values mean less optically mature or less space weathered. And here's our CF position here. And the swirls generally kind of hang around in this terrain where we have low maturities and also relatively bright and relatively low CF values compared to surrounding terrain. This is just for Reiner gamma, but it holds for other swirls as well. If we can compare things globally as well. And so now I'm showing 750 nanometer reflectance from the Kaguya MI versus CF position. All these gray dots are kind of the global distribution, and the CF position of the swirls are, in this case, in red. And takeaway from this is that, well, yeah, they might be a little bit brighter in some cases, but you generally follow the global trend. You might be slightly off the global trend, but you're kind of within the realm of reason here. Now, Paul Lucey was kind of the first one to recognize that our CF, as we measure with Diviner, is affected to some degree by space weathering. And he just submitted a paper to Icarus in the Icarus special issue. We provides OMAT-based CF correction. So we want to look at diviner data. We're only interested in composition. We want to get rid of the effects of space weathering. And so we can correct the global data set and the swirls using Paul's correction, which is just CF plus OMAT minus 0.285. That's the correction. When we do that for the global data set, we just kind of see a general shift to shorter wavelengths, which is what we'd expect. The CF, the effect of space weathering on the diviner CF is to shift it to longer wavelengths. So we see a shift to shorter wavelengths. And then we actually see some separation of the swirls from the global trend once we correct all this data. And this actually makes sense. Swirls in general compared to the global data are brighter and they are less mature. They have higher OMAT values compared to the whole global trend. So we're actually correcting the swirls less than we are the rest of the planet on average, and so we see some separation of the swirls in the global trend. We spent a lot of time in the diviner team thinking about why we're even sensitive to CF, and I think it was probably 5 or 6 years ago that Josh Banfield in a diviner team meeting brought up the idea, well, it was probably just albedo related. Darker surfaces, you're going to get a different thermal gradient than brighter surfaces, and so then that thermal gradient is going to affect the CF position. Paul, in his paper, actually talks about that, goes into that in a lot more detail in his paper, but we can actually test this. So here is a plot that we collected a bunch of spectra of quartz in the lab. My hat tip to Catherine Shirley, one of my graduate students. We ground up a bunch of quartz to less than 64 microns. We took reflectance spectra of them and measured the reflectance at 750 nanometers. And then we measured the CF position. We measured the infrared spectra in a simulated lunar environment chamber at Stony Brook. And the difference between these dots here, and each one of these dots is a measurement, is we just added tiny, minute amounts of amorphous black carbon. So we're not changing the composition. We're not changing the compositional measurement. All we're doing is darkening the samples. And you see a really nice trend here of CF position getting longer as you reduce the albedo. So we're setting up a different thermal gradient that we see on the surface of the moon, and we're shifting the CF. Interestingly, I'm not showing the data here, but interestingly, if we measure the spectra in just an ambient terrestrial environment, we see no shift in the CF as well. So we test this, and then the result is we see this kind of strong correlation between albedo and CF independent of composition. But the main driver of the CF position is still composition. So the fact that the swirls have a visibly higher albedo is affecting the CF, and that's really driving diviner's observations of the swirls. Okay, so we see a CF shift at both the Highlands and Mare swirl sites. I go into this in the 2015 paper quite a bit. The CF sensitivity is due to albedo variations, and we can think about what this all means in terms of the hypotheses that have been proposed. This, I would say, is consistent with the kind of atypical space weathering related to the solar wind deflection and continued impact bombardment, but it's also still consistent with some of these other models, and we have to do some more testing. If this is true, though, the implication is that the solar wind sputtering implantation is either more important than the micrometeoroid bombardment, or that the micrometeoroid bombardment is necessary but not sufficient for true optical maturation. But we need to look at these in a little bit more detail to really kind of separate out this mechanism from the others. And so for that, we can think about things like roughness and thermal properties. So if you look at some of these other mechanisms, the dust lofting and microcomet or meteorite swarm hypotheses or mechanisms would be expected to alter the surface regolith at kind of centimeter to millimeter scales, whereas a regolith disturbance by bombardment would probably make a surface rougher, and dust lofting would make the surface smoother. So what can we say with diviner data? We look at diviner daytime data measurements and Paul Haynes' roughness model, and we can maybe say something about this. So here are data for 2 swirls. Reiner Gamma we showed in our paper earlier this year. ARI, we just processed this data. What you're looking at is the change in temperature between band 3 in diviner and band 6, which is at much longer wavelengths. So we're measuring essentially surface anisothermality. And this isothermality is highly correlated to surface roughness, RMS surface roughness. And these lines here are contours every 5 degrees from 10 degrees surface roughness all the way to 40 degree surface roughness. And in bold here, I have 25 degree and 40 degree surface roughness. And on each plot, you're seeing measurements from on the swirl and off the swirl, in this case, Reiner gamma, and in this case, Airy. And what you see is that there's basically no statistical difference at all in the roughness off the swirl and on the swirl. And that they plot kind of in this 25 to 30 degree RMS surface roughness area, which is very typical of lunar regolith. So at least these two swirls are indistinguishable in terms of their surface roughness from kind of general lunar, from the general moon. Okay. So what we would see here is that both off swirl and on swirl sites have these kind of RMS surface roughnesses that are typical of lunar regolith, and there is, and we can't use this as a mechanism to, any mechanism that would change the roughness of the swirls. We have to account for that because we don't see it in the data. We can also look at nighttime cooling. So this is a plot put together, or a map put together by Josh Banfield, where we're looking now at just the change in temperature relative to the whole scene average at night. And here's the Reiner gamma swirl region, which I showed in my first plot. And you can maybe make out a darker, slightly lower temperature region around the area of the swirl compared to the regional terrain. What really pops out are these little craters, which have higher nighttime temperatures. The Reiner gamma swirls, on average, only about a half a degree cooler than the surrounding terrain at night. So we can look at a nighttime cooling model, again provided by Paul Hain, to shed light on swirl formation mechanism. Can a lofted dust pile account for the temperature difference at the swirl sites? Right? So if we have this dust lofting mechanism that's going to move dust around, we're going to be changing the surface properties, and maybe that can account for this different temperature. So here's a nighttime cooling model. In this case, we're looking off swirl and on swirl. The only difference is in an albedo value of 0.09 on the swirl or off the swirl, and 0.14 on the swirl. And again, here on the data points with error bars are the actual diviner data. And basically, you can account, what this says is you can account for the slight difference in temperature between Reiner gamma swirl and the surrounding off swirl terrain only by changing the albedo only due to the albedo difference between the swirl and the non-swirl region. If we added a 2 millimeter lofted dust pile to the Reiner gamma swirl, and that had a thermal inertia that was something about 50% of typical lunar regolith that you might expect for this type of lofted dust pile, then you end up with a nighttime cooling rate and surface temperatures that are much too low compared to what we measure with the diviner data. Okay, and there's one more thing we can look at here. These are ground-based telescopic measurements of Reiner gamma. You can see it here in the mid-infrared during a lunar eclipse. And so we see Reiner gamma, we see it, the eclipse is coming in, it is getting darker and darker, and we actually can't find Reiner gamma anymore, and so they're moving around here. And then we're going to come out of the eclipse, and we're going to see Reiner gamma again. Can we play that one more time as we're going so I can explain what's going on? Eclipse observations are incredibly important because they really get to the thermophysical properties of the epiregolith, the top millimeters of the surface. And during the eclipse, if we saw a dust layer or a fine layer at the surface, we'd expect during the eclipse to see a thermophysical or temperature anomaly related to the swirl. As you can see, oops, oh, I just killed it, sorry. As you can see in the nighttime, as we go into the eclipse, the swirl feature disappears, and we can't see it compared to the surrounding terrain. So there really is no, there really can't be a finely structured feature or layer at Reiner gamma, and these eclipse observations constrain that really well. Okay, so Reiner gamma is cooler. The nighttime cooling model suggests that even a kind of a 2 millimeter fluffy layer results in swirl temperatures that are much too cold to explain the diviner observations. The eclipse cooling observations constrain the swirl layer to less than a millimeter. And so all of these things point to the idea that the solar wind standoff model is probably the most correct, because any other mechanism, really, you have to, if you want to invoke one of these to form the swirls, you have to account for the diviner CF measurements, the roughness properties, and the thermophysical properties. All right, that's it. Thank you.
Any questions? Anybody want to stand up for one of the other models? If you dare.
I just have a basic question in terms of the roughness.
Sure.
I mean, I guess the question is, how rough? It seems to me like in terms of space weathering, you can have kind of a generation of fine grains, which can also sort of affect, what you see in UV and FUV.
Sure.
So at what degree do you...
Yeah, so there are different scales of roughness, right? I mean, Lola can measure, meter scale roughnesses. With visible light, we can measure kind of, sub-millimeter scales. And we're talking about centimeter scale surface roughnesses, where this type of roughness is being used to constrain a model that would change the roughness of the swirls at those types of centimeter scales, or sub-centimeter scales.
Okay.
All right, thank you.
Good, thank you. Okay, so the next talk